It is late, and you have arrived here. Whether your day was kind or difficult, this hour is yours to rest. Let the small worries that climb into the dark slip back beneath the surface. Tonight, we will drift very slowly into the deep, slow story of comets and asteroids, the small, icy, and rocky bodies that quietly travel through the long, patient dark of the solar system far beyond the warmth of the sun. This is the Circadian Institute. We exist for the long nights, for the in-between hours when the body is ready to sleep, but the mind is still moving. Tonight, our subject is the deep, slow story of comets and asteroids, the great main belt between Mars and Jupiter, the dwarf planet Ceres, the bright asteroid Vesta, the Trojan companions of Jupiter, the famous Halley's Comet returning every 76 years, the great comets that arrive once in a generation, the distant Kuiper Belt at the edge of our planetary neighborhood, and the vast spherical Oort Cloud at the very edge of the sun's quiet influence. If this kind of slow journey suits you, subscribing keeps these nights arriving. Tonight, we will travel together through the small bodies of the solar system. We will visit the great main asteroid belt between Mars and Jupiter, the dwarf planet Ceres, the bright reflective surface of Vesta, the Trojan asteroids that share Jupiter's orbit, the famous Halley's Comet, the great rare comets that arrive once in a generation, the distant icy bodies of the Kuiper Belt, and the vast spherical Oort Cloud at the very edge of the sun's quiet domain. There is no hurry. We have all the time we need. To begin tonight's journey, we will visit the broader family of small bodies that share our solar system. There are perhaps 1 million asteroids large enough to be tracked by telescope, and many billions of smaller bodies. There are also countless comets, most of them resting quietly in the deep cold of the outer solar system, far beyond the warmth of the sun. These small bodies are the ancient remnants of the formation of the solar system. About 4.5 billion years ago, a vast cloud of cosmic gas and dust slowly collapsed under its own gentle gravity. Most of the material gathered into the sun. The remaining material formed the planets, the moons, and the great cloud of small leftover pieces that we now call asteroids and comets. The fundamental difference between an asteroid and a comet is what they are made of and where they formed. Asteroids are mostly rocky and metallic. They formed in the warmer inner solar system, close enough to the sun that ice could not survive on their surfaces. Comets are mostly ice and dust. They formed in the cold outer solar system, where ice could remain solid for billions of years. Together, asteroids and comets are sometimes called the small bodies of the solar system. They are small only by comparison to the planets. The largest asteroid, Ceres, is nearly 1,000 kilometers across, large enough to be considered a dwarf planet. The largest known comet nucleus is also more than 100 kilometers across. To human scale, these are vast worlds. Most of the asteroids in the solar system orbit the sun in a great ring called the main asteroid belt. This ring sits between the orbits of Mars and Jupiter, far enough from the sun that ice can sometimes survive in shadowed places, but close enough that most surfaces are dry rock and metal. The main belt holds nearly all of the largest asteroids ever discovered. Comets, by contrast, mostly live in two great cosmic reservoirs far beyond Pluto. The first reservoir is called the Kuiper Belt, a flat ring of icy bodies extending from about 30 to 50 times Earth's distance from the sun. The second reservoir is called the Oort Cloud, a vast spherical shell of distant icy bodies extending nearly halfway to the nearest star. Occasionally, the gentle gravitational pull of a passing star or a giant planet nudges a comet from one of these distant reservoirs. The comet falls slowly inward toward the Sun, taking thousands or millions of years to make the journey. As it approaches the warm inner solar system, its surface ice begins to vaporize, and the comet develops the bright glowing coma and the long flowing tail that human astronomers have observed for thousands of years. Most asteroids never come close to Earth. The vast majority remain quietly in the main belt or in the orbits of giant planets, far from our world. A small number, however, have orbits that bring them into the inner solar system. These are called near-Earth objects, and they are carefully tracked by astronomers around the world. The first asteroid was discovered on the very first night of the 19th century. On the 1st of January in 1801, the Italian astronomer Giuseppe Piazzi was working at the Palermo Observatory in Sicily. He noticed a small point of light moving slowly against the background stars. He thought he had found a new comet. Later observations showed that the new object orbited the Sun in a nearly circular path between Mars and Jupiter. He had discovered Ceres. After Ceres, 3 more large asteroids were discovered in quick succession. Pallas was found in 1802 by the German astronomer Heinrich Olbers. Juno was found in 1804 by Carl Harding. Vesta was found in 1807, again by Olbers. For nearly 40 years, these 4 objects were thought to be the entire population of the new class of small bodies between Mars and Jupiter. In 1845, a 5th asteroid was discovered, then a 6th, a 7th, and 8th. By the end of the 19th century, hundreds of asteroids had been catalogued. By the end of the 20th century, the count had passed 10,000. Today, more than 1 million asteroids have been discovered and given orbital elements, and astronomers continue to find more every night. Comets have been observed by human eyes for far longer than asteroids. Ancient Chinese astronomers kept careful records of comet appearances going back more than 2,000 years. Babylonian astronomers tracked comets nearly as far back. Each great comet that crossed the night sky was carefully described, sometimes with mythological significance, sometimes with simple wonder at the strange wandering visitor. Tonight's journey will move slowly through the rich variety of these small bodies. We will begin in the main asteroid belt itself, with its largest and most famous members. Then we will move outward to the Trojan asteroids that share Jupiter's orbit, and inward to the near-Earth asteroids that pass close to our world. After that, we will turn to the comets, the great cosmic visitors that arrive from the deep cold beyond. Because asteroids and comets are so small compared to planets, they have weak gravity. Most are not perfectly round. They have irregular potato-like or peanut-like shapes, sculpted slowly over billions of years by gentle collisions and the steady push of sunlight. Only the largest few, like Ceres and Vesta, have enough self-gravity to pull themselves into nearly spherical forms. Many asteroids and comets are also very dark. Their surfaces reflect only a small fraction of the sunlight that falls on them, sometimes as little as 3 or 4%. To human eyes, they would appear nearly as dark as charcoal. Astronomers detect them by careful long-exposure photography against the background of distant stars, watching for the slow motion that reveals a small body slowly orbiting the Sun. Despite their darkness, these small bodies are extraordinarily numerous. The total mass of all the asteroids in the main belt combined is only about 4% of the mass of our Moon. Yet the number of individual bodies is enormous, many millions large enough to be tracked, and likely many billions smaller still. The sheer cosmic count of small bodies in our solar system is far larger than the number of stars in our galaxy. Now, gently, we will turn our attention to the great main asteroid belt itself, where most of the rocky small bodies of the solar system quietly reside between the orbits of Mars and Jupiter. The main asteroid belt sits in a quiet ring around the Sun, between the orbits of Mars and Jupiter. The inner edge lies about 2.1 astronomical units from the Sun, where 1 astronomical unit is the average distance from Earth to the Sun. The outer edge lies about 3.3 astronomical units from the Sun. The belt itself spans about 180 million kilometers of cosmic distance. Despite the enormous number of asteroids in the main belt, the belt is mostly empty space. The asteroids are spread across such a vast cosmic volume that the typical distance between any two large asteroids is roughly 1 million kilometers, far greater than the distance between Earth and the Moon. Spacecraft sent through the belt have crossed it without difficulty. The cinematic image of a crowded asteroid field is a dramatic exaggeration. The total mass of the main asteroid belt is small. If all of the asteroids were combined into a single body, the result would be smaller than our Moon. About 1/3 of the total mass is contained in just one body, Ceres, the largest asteroid and the only dwarf planet in the inner solar system. Another 20% is in just 3 more, Vesta, Pallas, and Hygiea. The asteroids of the main belt are organized into several distinct families, each thought to be the fragments of a single ancestral body that broke apart in a slow, gentle collision long ago. The Themis family, the EOS family, the Coronis family, each is a group of asteroids sharing similar orbital elements and similar surface composition. There are dozens of families altogether, each one a slow cosmic puzzle. Asteroids are also classified by their surface composition. The most common type, called C-type, is dark and carbon-rich. About 3/4 of all known asteroids belong to this class. They are mostly found in the outer parts of the main belt. The next most common type, called S-type, is silicate-rich and somewhat brighter. They are mostly found in the inner parts of the belt. The small number, called M-type, are metallic. The main belt also contains some objects that behave like comets. They are called main belt comets. They look like ordinary asteroids most of the time, but occasionally they develop faint tails of vapor and dust, suggesting that they contain pockets of buried ice that sometimes vaporize. The first main belt comet was discovered in 1996. Today, several dozen are known. Astronomers learned a great deal about asteroids by sending spacecraft to visit them. The first close-up image of an asteroid was taken in 1991 when the Galileo spacecraft flew past the asteroid Gaspra on its way to Jupiter. 2 years later, Galileo encountered another asteroid, Ida, and discovered that it had its own tiny moon called Dactyl, the first known asteroid moon. Since then, many more asteroid moons have been discovered. Some asteroids have 1 moon, some have 2. The largest asteroid binary system is the dwarf planet Patroclus, a Trojan asteroid that consists of 2 nearly equal-sized bodies orbiting around their common center of mass. Astronomers estimate that perhaps 1 in 6 main belt asteroids has at least 1 moon. The shape of an asteroid depends on its size and history. Very small asteroids, those less than a few hundred meters across, can be loose collections of dust and rubble held together by their own faint gravity. Medium-sized asteroids, a few kilometers to a few tens of kilometers, are usually irregular potato-shaped. Only the largest asteroids, those several hundred kilometers across, have enough gravity to be nearly spherical. Asteroids rotate on their axes at varying speeds. Some asteroids spin once every few hours, others rotate once every few days. The fastest rotators are very small bodies, sometimes only a few hundred meters across, that complete a full rotation in less than 2 hours. The slowest known rotators take many weeks to turn once around their axes. The rotation of an asteroid slowly changes over time as gentle sunlight pushes asymmetrically against its irregular surface. The temperature on an asteroid in the main belt is cold by Earth standards. Surface temperatures typically range from around -70 degrees Celsius on the sunlit side to colder than -150 degrees on the shadowed side. The Sun, seen from the main belt, looks much smaller and dimmer than it does from Earth, a brilliant point of warm light, but no longer dominating the sky. Some asteroids in the main belt have very unusual orbits. The Hygiea group, for example, orbits the Sun in a special pattern that takes them around 3 times for every 2 orbits of Jupiter. This kind of orbital relationship is called a resonance. The Hygiea asteroids form a quiet triangular pattern in the outer main belt, slowly tracing the same shape across the cosmic dark for billions of years. Other parts of the asteroid belt are nearly empty. These regions are called Kirkwood gaps, named after the American astronomer Daniel Kirkwood, who first noticed them in 1866. The gaps occur at distances from the Sun where any asteroid would feel a regular gravitational pull from Jupiter. Over millions of years, these gentle gravitational nudges slowly clear the asteroids out of those orbits. The first spacecraft to orbit an asteroid was NEAR Shoemaker, which orbited the asteroid Eros in the year 2000. After more than a year of close observations, the spacecraft made a gentle, controlled landing on the surface of Eros, becoming the first probe ever to land on an asteroid. The cosmic touchdown happened on the 12th of February in 2001. More recent missions have visited even more challenging asteroids. The Japanese mission Hayabusa landed on the asteroid Itokawa in 2005 and successfully returned a small sample of asteroid dust to Earth. Its successor Hayabusa 2 visited the asteroid Ryugu in 2018 and returned an even larger sample. The American mission OSIRIS-REx visited the asteroid Bennu and brought back samples of dark carbonaceous material. These returned samples have given astronomers an extraordinary window into the early solar system. The grains of dust and small fragments of rock have remained essentially unchanged for 4.5 billion years. They contain the same chemical elements that built the planets, including water and complex carbon molecules, the same building blocks that may have contributed to the conditions for life on Earth. Now, gently, we will turn our attention to the largest member of the main belt, the dwarf planet Ceres, the only known dwarf planet in the inner solar system, and a quiet world with hidden surprises beneath its surface. Ceres is the largest object in the main asteroid belt and the only dwarf planet in the inner solar system. It is roughly 940 kilometers across, about the same size as the state of Texas, or about a quarter of the size of our moon. Ceres holds about one-third of the total mass of the entire main asteroid belt by itself. When Ceres was first discovered in 1801, it was classified as a planet. For nearly 50 years, the official planet count of the solar system included Ceres as the eighth planet, until astronomers began to realize that many similar small bodies were being discovered in the same region. Eventually, all of these objects, including Ceres, were reclassified as asteroids. Then, in 2006, Ceres was reclassified once again, this time as a dwarf planet, the same category as Pluto. Ceres orbits the Sun once every 4.6 Earth years. Its orbit lies near the middle of the main asteroid belt at an average distance of 2.77 astronomical units. Throughout its long journey around the Sun, Ceres travels at an average speed of about 17 kilometers per second. The path it traces through cosmic space is nearly circular. Ceres rotates on its axis once every 9 hours. This rapid rotation gives it a slightly flattened shape, with a polar diameter that is somewhat smaller than its equatorial diameter. The axis of rotation is nearly perpendicular to the orbital plane, which means that Ceres has very little seasonal variation. The Sun rises and sets in nearly the same way throughout the entire Cerean year. In 2015, the Dawn spacecraft arrived at Ceres after a long, quiet journey from Earth. Dawn became the first spacecraft ever to orbit a dwarf planet. Over the following years, Dawn carefully mapped the entire surface of Ceres in extraordinary detail. The spacecraft revealed a world far more interesting than astronomers had expected. The surface of Ceres is heavily cratered, like all ancient cosmic bodies that have spent billions of years exposed to the slow rain of space debris. The largest crater, called Kirwan, is about 280 kilometers across. Many of the craters on Ceres are remarkably well preserved, suggesting that the surface has been geologically quiet for a long time. Among the many craters on Ceres, one stands out for a strange and beautiful reason. The crater Ocator, about 90 kilometers across, contains several patches of brilliant white material that reflects far more sunlight than the surrounding dark surface. When Dawn first photographed these bright spots, they appeared so much brighter than their surroundings that the early images simply showed them as overexposed white pixels. Closer observations revealed that the bright patches in Ocator are deposits of salt, primarily sodium carbonate. The salts are thought to have been brought to the surface by briny water seeping up from below. As the briny water evaporated into the cosmic vacuum, the salts were left behind as bright white crystalline deposits. But the discovery suggested that Ceres has, or recently had, liquid water somewhere beneath its surface. In addition to the salts, Dawn also detected the presence of organic molecules on the surface of Ceres. Organic molecules are complex carbon-based compounds that, while not necessarily indicating life, are the chemical building blocks from which biological molecules can form. Their presence on Ceres is a quiet hint at the rich and varied chemistry of the early solar system. Beneath the surface of Ceres, astronomers believe, lies a layer of water-rich mantle. Some estimates suggest that as much as 25% of the mass of Ceres may be water, locked into icy minerals, perhaps existing as a deep-buried briny ocean, or both. If Ceres has even a partial subsurface ocean, it would join Europa, Enceladus, and a small number of other solar system bodies as worlds with liquid water far from the Sun. Ceres also has a very thin atmosphere of water vapor. The vapor was first detected by the Herschel Space Observatory in 2013. The amount of water vapor is small but persistent. It is believed to be released either by sunlight slowly vaporizing surface ice or by occasional small bursts of subsurface water making its way to the surface and vaporizing into the cosmic vacuum. The mountain called Ahuna Mons rises about 4 kilometers above the surrounding terrain on Ceres. It is unusually steep and isolated, surrounded by mostly flat surface. Astronomers believe that Ahuna Mons may be a cryovolcano, a volcano that erupts not with hot lava but with cold, briny water and slush. If so, it would be one of the few known cryovolcanoes anywhere in the solar system. Ceres receives only about 10% of the sunlight that Earth receives. Because it is so much farther from the Sun, the surface temperature on Ceres reaches at most minus 38 degrees Celsius at the equator on the sunlit side and far colder elsewhere. Much of the surface remains permanently shadowed in deep craters near the poles, where temperatures may stay below minus 200 degrees Celsius for billions of years. Inside those permanent dark craters near the poles of Ceres, water ice can survive indefinitely. Dawn discovered patches of bright ice in several such craters during its mission. The ice deposits are thin and patchy, but they represent some of the most exposed water ice anywhere in the inner solar system. The Dawn mission ended in 2018 when the spacecraft ran out of fuel by design. Dawn was left in a stable orbit around Ceres, where it will continue to circle the dwarf planet for many decades. The spacecraft itself is now a quiet, permanent satellite of Ceres, drifting in slow loops around the small, distant world it once explored. Ceres has been recognized as a place of significant scientific interest, and astronomers continue to plan future missions to study the dwarf planet in even greater detail. Some proposals involve landers that would touch down near the bright salt deposits in the Achater crater, sampling the chemistry of the surface and searching for further signs of past or present water activity. Now, gently, we will move from the dwarf planet Ceres to the second largest member of the main asteroid belt, the bright reflective world of Vesta, with its dramatic cosmic history. Vesta is the second largest object in the main asteroid belt. It is roughly 525 kilometers across, making it about half the size of Ceres but containing nearly the same total mass because Vesta is much denser. Vesta is also the brightest asteroid in the entire sky. On the rare nights when its position is favorable, it is the only asteroid that can be seen with the unaided human eye. Vesta was discovered in 1807 by the German astronomer Heinrich Olbers, who had also discovered Pallas 5 years earlier. Vesta was the fourth known asteroid, and Olbers found it by carefully comparing his nightly observations of the same region of the sky. Like Ceres and Pallas before it, Vesta was first thought to be a planet. Vesta orbits the Sun once every 3.6 Earth years at an average distance of about 2.36 astronomical units. Its orbital path is more elliptical than that of Ceres, taking it from about 2.1 to 2.6 astronomical units across each Vesta year. Vesta also rotates rapidly, completing one full rotation every 5¼ hours. The most striking feature of Vesta is the enormous crater that dominates its southern hemisphere. The crater, called Resilvia, is about 500 kilometers across, almost the same as the diameter of Vesta itself. The crater was created by an enormous impact billions of years ago that removed nearly 1% of the entire mass of Vesta, sending vast amounts of debris into surrounding cosmic space. At the center of the Hygiea crater rises a central mountain peak that is one of the tallest known mountains in the solar system. It stands about 22 kilometers high, more than 2.5 times the height of Mount Everest on Earth. The peak was formed during the slow rebound of the cosmic impact that created the surrounding crater. The debris that was thrown out of Vesta during the Hygiea impact did not vanish into deep space. Most of it remained in the main asteroid belt, gradually breaking apart and forming what is now called the Vesta family, a group of small asteroids that share Vesta's orbital characteristics and surface composition. Astronomers have identified more than 15,000 members of the Vesta family. Some of the smaller fragments of the Vesta impact have eventually fallen to Earth as meteorites. These special meteorites are called HED meteorites, short for Howardite, Euclidite, and Diogenite. They make up roughly 6% of all meteorite falls observed on Earth. Each HED meteorite found is a small piece of Vesta brought home, allowing detailed laboratory study of the asteroid without sending a spacecraft. Vesta has a layered internal structure similar to that of a small planet. There is a metallic iron-nickel core at the center, a silicate mantle in the middle, and a basaltic crust on the outside. Vesta is therefore sometimes called a protoplanet, a small body that began the process of forming a planet but never grew large enough to complete it. The core of Vesta is about 200 kilometers across. The surface of Vesta has a creamy tan color, brighter and warmer than the dark gray surfaces of most other asteroids. The high reflectivity of Vesta is caused by the basaltic minerals on its surface, which reflect light efficiently back into space. This is what makes Vesta the brightest known asteroid as seen from Earth. The Dawn spacecraft, the same mission that later visited Ceres, also visited Vesta. Dawn arrived at Vesta in 2011 and spent 14 months in orbit around the asteroid. The spacecraft mapped the entire surface in extraordinary detail, measured the gravitational field, and discovered features that had been completely unknown before. Among the discoveries made by Dawn was a second enormous crater on Vesta, partly overlapping with Hygiea. The older crater called Venenea is about 400 kilometers across. The two craters together cover most of the southern hemisphere of Vesta. Together they reveal that Vesta has experienced at least 2 enormous cosmic collisions in its long, quiet history. In the equatorial regions of Vesta, Dawn discovered a series of long parallel grooves that wrap around much of the asteroid. The grooves are believed to be cosmic stress fractures created by the same enormous impacts that formed Hygiea and Venenea. The shock waves from those collisions traveled through the entire body of Vesta and left their mark in the surface near the equator. Despite all of these dramatic features, Vesta has been geologically quiet for a very long time. The HED meteorites suggest that Vesta solidified within the first 100 million years of solar system history. Since then, the surface has been gradually shaped by slow, steady cosmic impacts, but no internal volcanic activity has occurred for billions of years. Compared to Ceres, Vesta has very little water. Vesta formed in a hotter inner part of the early main belt, where most water and ice would have been driven away by the warmth of the young sun. The surface of Vesta is essentially dry, although small amounts of water-bearing minerals have been detected in some regions. Vesta is sometimes considered the smallest member of a separate category called terrestrial protoplanets. These were the building blocks of the inner planets, bodies large enough to differentiate into core, mantle, and crust, but never large enough to grow into full planets. Most other terrestrial protoplanets were eventually consumed in the formation of Mercury, Venus, Earth, and Mars. Vesta is among the few that survived intact. Vesta is sometimes visible from Earth without a telescope. When it is at its closest approach and at opposition, when Earth lies between Vesta and the Sun, Vesta can reach a brightness of magnitude 5.1, bright enough to be seen as a faint point of light from a dark sky location. Many amateur astronomers have observed Vesta this way. Now, gently, we will move from Vesta to several other large members of the main asteroid belt: Pallas, Hygiea, and the other big four asteroids that together hold most of the mass of the entire belt. After Ceres and Vesta, the third largest member of the main asteroid belt is Pallas. Pallas is roughly 512 kilometers across, only slightly smaller than Vesta. It was discovered in 1802 by the German astronomer Heinrich Olbers, the same astronomer who would later discover Vesta. Pallas was the second known asteroid, and at the time of its discovery, it was thought to be a planet. Pallas has an unusual orbit compared to most other large asteroids. It is significantly tilted, about 35 degrees away from the average orbital plane of the planets. Most asteroids orbit close to the same flat plane as the planets, called the ecliptic. Pallas instead spends much of its time well above or well below the ecliptic, making it harder to observe and unusual among large asteroids. The shape of Pallas is also unusual. Unlike Ceres, which is nearly spherical, Pallas is more irregular and asymmetric. It is sometimes described as a triaxial ellipsoid, meaning it has three different axes of length. The asymmetric shape is thought to be the result of major impacts billions of years ago that altered the original near-spherical body. The surface of Pallas is dark. It belongs to the C-type or carbonaceous class of asteroids, bodies that are rich in carbon-bearing minerals and hydrated silicates. The surface reflects only about 12% of the sunlight that reaches it. Astronomers have detected a small amount of water-bearing material on Pallas, suggesting that it formed in the cooler outer regions of the early main belt. The fourth largest object in the main asteroid belt is Hygiea. Hygiea is roughly 430 kilometers across and was discovered in 1849 by the Italian astronomer Annibale de Gasparis, like Pallas. Hygiea is a dark carbonaceous asteroid. It orbits the Sun in the outer part of the main belt, at an average distance of about 3.14 astronomical units. In 2019, careful telescope observations revealed that Hygiea is nearly perfectly spherical, much more so than astronomers had previously believed. This means Hygiea may technically meet all of the criteria for being classified as a dwarf planet. If accepted, Hygiea would become the smallest known dwarf planet and the second dwarf planet in the main asteroid belt after Ceres. Together, Ceres, Vesta, Pallas, and Hygiea contain about half of the entire mass of the main asteroid belt. The remaining half is distributed among more than 1 million smaller bodies, ranging from a few hundred kilometers across down to small house-sized fragments. The four largest are sometimes collectively called the Big Four. There are also several other notable large asteroids that, while smaller than the Big Four, are still significant cosmic bodies. Eunomia, the largest member of the S-type or stony class, is about 250 kilometers across. Davida is a large, dark, carbonaceous body about 300 kilometers across. Interamnia, another large, dark asteroid, is about 350 kilometers across. Each of these large asteroids has its own gentle history. Most have been hit by smaller cosmic impacts many times over their long lives. Some have small moons. Some have generated families of smaller fragments that share their orbits. All have rotated quietly under the same dim, distant sun for billions of years. In addition to the Big Four, there are many medium-sized asteroids in the main belt. These bodies range from about 100 to 250 kilometers across. Some are well known to amateur astronomers because they have been studied carefully for centuries. Others are newer discoveries found only in recent decades by automated telescope surveys. Many of the largest asteroids have been given names from mythology, history, and even modern culture. Ceres is named after the Roman goddess of agriculture. Pallas is named after Pallas Athena, the Greek goddess of wisdom. Vesta is named after the Roman goddess of the hearth. Hygiea is named after the Greek goddess of health. The tradition of naming asteroids after gods and heroes continues today, although modern asteroids are also named after places, people, and concepts. Astronomers have estimated that there are perhaps 200 asteroids in the main belt larger than 100 kilometers across. There are perhaps 1,000 larger than 30 kilometers, and many tens of thousands larger than 10 kilometers. Below that size, the count rises rapidly into the millions. The smallest known asteroids are only a few meters across. The total number of small bodies in the main belt is enormous. Recent automated telescope surveys, especially those from facilities like the Pan-STARRS Observatory in Hawaii and the future Vera Rubin Observatory in Chile, are continuing to discover new asteroids at an extraordinary rate, sometimes hundreds per night. The full census of the main belt may take many more decades to complete. Among the most interesting asteroids in the main belt are those classified as M-type, bodies that appear to be largely metallic, composed mostly of iron and nickel. These asteroids may be the exposed cores of ancient larger bodies that were stripped of their outer layers by enormous cosmic collisions billions of years ago. The largest known M-type asteroid is Psyche, about 230 kilometers across. Psyche is currently the destination of an active spacecraft mission. The Psyche probe, launched by NASA in 2023, is slowly traveling through deep space toward its target. It is expected to arrive at Psyche in 2029. Once there, it will spend more than 2 years quietly orbiting the metallic asteroid and studying its composition in detail. The variety of asteroids in the main belt reflects the variety of conditions in the early solar system. Different parts of the belt formed at different distances from the young sun, with different temperatures and different chemistries. Each surviving asteroid is a quiet record of the conditions in its small region of the early solar system, preserved for 4.5 billion years. Now gently we will move from the main belt outward to a special group of asteroids that share Jupiter's orbital path, the Trojan asteroids that travel quietly ahead of and behind the great gas giant. The Trojan asteroids are a special group of small bodies that share Jupiter's orbital path around the Sun. They do not orbit Jupiter directly. Instead, they orbit the Sun in the same path as Jupiter, but they remain locked in two distinct gravitational pockets, one ahead of Jupiter and one behind. These pockets are known as the L4 and L5 Lagrange point. The Lagrange points are stable locations in space where the gravitational pull of two large bodies, in this case the Sun and Jupiter, combine in such a way that smaller objects can remain in a steady balanced position over very long periods of time. The Trojan asteroids have been quietly resting in these gravitational shelters for billions of years. The first Trojan asteroid was discovered in 1906 by the German astronomer Max Wolf. The asteroid was named Achilles after the great hero of the Trojan War. Following this naming convention, asteroids in the L4 cluster, the one leading Jupiter, were given names of Greek warriors from the Trojan War. Asteroids in the L5 cluster, the one trailing Jupiter, were given names of Trojan warriors. Today, more than 12,000 Trojan asteroids have been cataloged, and the total population is estimated to be roughly equal to the population of the entire main asteroid belt, perhaps 1 million bodies larger than 1 kilometer across. The L4 group, leading Jupiter, contains about twice as many bodies as the L5 group, trailing Jupiter. The reason for this asymmetry is not fully understood. The largest known Trojan asteroid is named Hector. It is a strange irregular body about 400 kilometers across, shaped like a peanut or a dumbbell. Hector is so elongated that some astronomers have suggested it may actually be two large bodies in contact with each other, a contact binary that gently came together long ago and never separate. The second largest Trojan, Patroclus, is even more interesting. Patroclus is a binary system, two bodies of nearly equal size, about 112 kilometers each, that orbit each other slowly, while both revolving around the Sun in Jupiter's L5 Lagrange point. The two bodies orbit one another over a period of about 4 days. Patroclus is one of the few known equal-mass binary asteroids. Most Trojan asteroids are very dark and red in color. Their surfaces reflect only about 3 to 5% of the sunlight that reaches them, making them among the darkest objects in the solar system. The red coloring is thought to come from organic compounds, carbon-based molecules that formed in the cold outer solar system and have remained on these surfaces for billions of years. The reddish color and dark surfaces of the Trojans suggest that they did not form where they currently reside. Instead, astronomers believe that the Trojans formed much farther out in the solar system, perhaps in the same general region as the comets and the Kuiper Belt objects. They were later captured into Jupiter's Lagrange points during the early reorganization of the solar system, when the giant planets slowly migrated to their current orbit. The NASA spacecraft Lucy, launched in 2021, is currently on a long, quiet journey to visit several Trojan asteroids. Lucy will be the first spacecraft ever to visit the Jupiter Trojan. The mission is named after the famous fossil of the early human ancestor, a poetic reference to the idea that the Trojans are themselves cosmic fossils, preserving the conditions of the early solar system. The Lucy mission will visit at least 7 different Trojan asteroids over the course of more than a decade. The first close encounter is scheduled for 2027, when Lucy will fly past the asteroid Eurybates and its small moon Quetta. Subsequent encounters will visit additional Trojans through the early 2030s. The Trojan asteroids are stable in their Lagrange points over very long timescales, far longer than the current age of the solar system. They will likely remain quietly trapped near Jupiter's orbital path for billions of years to come, slowly orbiting the Sun in their gentle gravitational shelters as the solar system continues its long, quiet evolution. Other planets in the solar system also have Trojan asteroids, although in much smaller numbers than Jupiter. Mars has at least 9 known Trojans. Earth has 2 known Trojan asteroids, both very small, only a few hundred meters across. Venus has at least 1 known Trojan, and Uranus and Neptune each have several. The total population of non-Jupiter Trojans is far smaller than the Jupiter group. Trojan asteroids associated with planets other than Jupiter are typically smaller and harder to detect because their gravitational shelters are smaller. Even so, the discovery of Trojans for other planets has confirmed that the Lagrange point phenomenon is a general feature of orbital dynamics throughout the solar system. The dark surfaces of the Trojan asteroids hold a particular astronomical interest. Because they are so dark, they absorb most of the sunlight that reaches them rather than reflecting it. The absorbed energy slowly warms the surface and is later released as faint infrared radiation. This thermal glow has been detected by space-based infrared telescopes, allowing astronomers to estimate the sizes of many Trojans even when their reflected light is too faint to measure precisely. Some Trojans appear to have small fragments and dust trails associated with them, suggesting that they have experienced gentle collisions over time. The dust trails are small and faint, but they are detectable with sensitive observations. The collisional history of the Trojan groups is an active area of cosmic research. The Trojan groups are an example of how gravity creates quiet, stable patterns throughout the solar system, even far from any single body. The mathematical patterns of orbital mechanics shape the locations of these asteroids as surely as the more familiar gravitational pull of the Sun shapes the orbits of the planets themselves. Now, gently we will move from the distant Jupiter Trojans inward to a different group of asteroids, those that approach close to our own planet's orbital neighborhood, the near-Earth asteroids. Near-Earth asteroids are a small but significant group of asteroids whose orbits bring them relatively close to Earth. They are usually defined as asteroids whose closest approach to the Sun is less than 1.3 astronomical units. This means that at some point in their orbital paths, they pass through the inner solar system where Earth and the other terrestrial planets reside. There are 3 main families of near-Earth asteroids, distinguished by the shapes of their orbits. The Apollo family is named after the asteroid Apollo, discovered in 1932. Apollo asteroids have orbits that cross Earth's orbit and that average a distance from the Sun greater than that of Earth. They spend most of their time outside Earth's orbit but periodically dip inward. The Aten family is named after the asteroid Aten, discovered in 1976. Aten asteroids have orbits that cross Earth's orbit, but that average a distance from the Sun less than that of Earth. They spend most of their time inside Earth's orbit and only periodically swing outward. The Aten group is the smallest of the 3 near-Earth families. The Amor family is named after the asteroid Amor, discovered in 1932. Amor asteroids have orbits that approach Earth's orbit closely but do not actually cross it. They orbit entirely outside Earth's orbital path. Amor asteroids are sometimes called Mars crossers because many of them do cross the orbit of Mars. A 4th recently recognized family is called the Atira asteroids. These bodies have orbits entirely inside Earth's orbit, which means they are always closer to the Sun than Earth is. Hygiea asteroids are very difficult to observe because they always appear close to the Sun in the sky. Only a few dozen Hygieas are currently known. The total number of near-Earth asteroids currently known is more than 30,000. The vast majority of these are very small bodies, less than 100 meters across. Only about 1,000 near-Earth asteroids are larger than 1 kilometer in diameter. Astronomers estimate that nearly all of the largest near-Earth asteroids have now been discovered, while many smaller ones remain to be found. Most near-Earth asteroids are not in stable orbits. Their close encounters with Earth and other inner planets gradually change their paths over time. The typical lifetime of a near-Earth asteroid in its current orbit is only a few million years, short by cosmic standards. Most are eventually either ejected from the inner solar system, captured by a planet, or collide with one. Because near-Earth asteroids have short lifetimes in their current orbits, the population must be continuously replenished. The replenishment comes mainly from the main asteroid belt, slow, gentle gravitational nudges from Jupiter, combined with subtle effects from sunlight pushing asymmetrically against rotating asteroid surfaces, gradually push small bodies from the main belt into orbits that approach the inner planets. Astronomers carefully track all known near-Earth asteroids using ground-based and space-based telescopes. Each new observation allows the orbit to be calculated more precisely, so that the asteroid's future positions can be predicted decades or even centuries into the future. This careful long-term tracking is one of the great quiet achievements of modern astronomy. Some near-Earth asteroids are classified as potentially hazardous asteroids, or PHA. These are bodies larger than about 140 meters in diameter that have orbits which can bring them within about 7.5 million kilometers of Earth. Roughly 2,000 asteroids are currently classified this way. None of them are predicted to actually collide with Earth in the foreseeable future. In 2022, NASA successfully tested the first dedicated planetary defense mission. The Double Asteroid Redirection Test, or DART spacecraft, was deliberately crashed into a small moon of the asteroid Didymos called Dimorphos. The impact slightly changed the orbit of Dimorphos around Didymos, demonstrating that a future asteroid threat could in principle be deflected by a similar gentle nudge. Many near-Earth asteroids are also of great scientific and economic interest because of their accessibility. They are easier to reach with spacecraft than the more distant main belt asteroids. Several space agencies and private companies have proposed missions to study and possibly even mine resources from near-Earth asteroids in the future. The Hayabusa 2 spacecraft visited the near-Earth asteroid Ryugu in 2018. Ryugu is a dark carbon-rich asteroid about 900 meters across, shaped like a spinning top. Hayabusa 2 spent nearly a year and a half in close proximity to Ryugu, deploying small landers, taking detailed surface measurements, and collecting 2 separate samples that were later returned to Earth. Similarly, the OSIRIS-REx spacecraft visited the near-Earth asteroid Bennu in 2018. Bennu is also a dark carbonaceous body about 500 meters across, similar in many ways to Ryugu. After more than 2 years of close observations, OSIRIS-REx collected a sample from the surface of Bennu and returned it to Earth in 2023. Both Ryugu and Bennu turned out to be much rougher and more rocky than expected. Their surfaces are covered with large boulders rather than the fine dust that astronomers had originally predicted. Both bodies are also less dense than expected, suggesting that they are loose collections of rubble held together by faint gravity rather than solid, coherent objects. The samples returned from Ryugu and Bennu have given scientists a remarkable window into the chemistry of the early solar system. The samples contain water-bearing minerals, organic molecules, and even amino acids, some of the basic building blocks of biological chemistry. Studying these samples helps scientists understand the chemical environment in which Earth and the other planets formed. Now, gently, we will move outward from the near-Earth space to a strange family of asteroids that orbit even farther from the Sun than Jupiter, the Centaurs and the distant asteroids of the outer solar system. Beyond the orbit of Jupiter, in the outer solar system, lies a strange and small family of bodies called the Centaurs. The Centaurs orbit the Sun between Jupiter and Neptune in a region where most of the small bodies are either ice-rich comets or distant Kuiper Belt objects. Centaurs are unusual because they share characteristics of both asteroids and comets. The first Centaur was discovered in 1977. The American astronomer Charles Kowal noticed a slow-moving object far beyond the orbit of Saturn. The object was named Chiron after the gentle, wise centaur of Greek mythology. Chiron is roughly 220 kilometers across, large enough that some astronomers have suggested it might qualify as a small dwarf planet. Following the discovery of Chiron, more centaurs were gradually identified. The next significant find was the centaur Pallas, discovered in 1992. Pallas is smaller than Chiron, about 150 kilometers across, and is one of the reddest known objects in the solar system. The deep red color is thought to come from organic compounds on the surface that have been processed by long exposure to cosmic radiation. Today, more than 500 centaurs are known. They have a wide variety of orbital parameters, sizes, and colors. The largest centaur, called Chariklo, is about 250 kilometers across. Chariklo has the unusual distinction of being the smallest known body in the solar system to possess its own ring system. Two narrow, dense rings were discovered around Chariklo in 2013. The discovery of rings around Chariklo was a complete surprise. Until then, ring systems were known only around the four giant planets, Jupiter, Saturn, Uranus, and Neptune. The rings around Chariklo, while much smaller and fainter, demonstrated that even small bodies can sustain ring systems for some period of time. The second, smaller centaur, called Chiron, was later found to also have material orbiting it. Centaurs sometimes show comet-like behavior. As Chiron approached its closest point to the Sun, astronomers detected a faint coma of dust and gas surrounding it, a hallmark of comet activity. Several other centaurs have shown similar activity over time. The activity reflects their composition, which includes a substantial amount of ice that can vaporize when warmed by sunlight. Most centaurs are believed to have originated in the Kuiper Belt, the great ring of icy bodies beyond Neptune. They were gradually moved into their current orbits by gentle gravitational interactions with the giant planets, especially Neptune. The orbits of centaurs are not stable. Most will eventually be either ejected from the solar system entirely, captured into different orbits, or pulled inward toward the inner planets where they may become short-period comets. The expected lifetime of a centaur in its current orbit is only a few million years, short compared to the 4.5 billion year age of the solar system. This means that the Centaurs we observe today must be relatively recent arrivals from the Kuiper Belt. The population is constantly being replenished as new bodies are gradually pushed inward from the more distant outer reservoir. In addition to the Centaurs, there are other distant asteroid-like bodies in the outer solar system. The Damocloids are bodies in highly elongated orbits that resemble the orbits of long-period comets. They are thought to be inactive or extinct comet nuclei whose surface ice has been entirely depleted over time. Damocloids are difficult to distinguish from true asteroids by appearance alone. Some distant asteroids are found in the outer parts of the asteroid belt and beyond. The asteroid Ida, discovered in 1984, has its own small moon called Dactyl, discovered by the Galileo spacecraft. Other distant binary asteroids have been found in similar configurations, suggesting that small companions are not uncommon in the outer asteroid populations. The cooler temperatures of the outer asteroid belt allow some asteroids there to retain water ice on or beneath their surfaces. The asteroid Themis, for example, has been observed to have a thin layer of water ice on its surface. The presence of ice on a main belt asteroid is unusual, but it suggests that water can survive longer than expected on cosmic bodies in this region. Some asteroids are extremely far from the Sun. The asteroid Eris, although technically classified as a Kuiper Belt object and dwarf planet, was originally catalogued among the distant asteroids. Eris orbits the Sun at an average distance of about 68 astronomical units, far beyond Neptune. The discovery of Eris in 2005 led directly to the reclassification of Pluto as a dwarf planet. Beyond the Centaurs, the population of small bodies grades smoothly into the Kuiper Belt and the more distant scattered disk. The boundaries between these populations are not always sharp. The same small body can be classified differently depending on the precise definition used and the most recent orbital observations available. The colors of the Centaurs and the more distant Kuiper Belt objects span a remarkable range. Some are deep red, like Pholas, others are pale gray or even slightly bluish. The variations in color reflect differences in surface composition and processing history. The reddest objects are believed to have surfaces rich in irradiated organic compounds, while the bluer objects may have fresher, cleaner surfaces. Future telescope surveys, especially those conducted by the upcoming Vera Rubin Observatory in Chile, are expected to dramatically increase the number of known centaurs and distant asteroids over the coming decade. Many thousands of new objects in this region are likely to be discovered, painting a far more complete picture of the small bodies of the outer solar system. The Centaurs occupy a quiet transitional zone in the solar system. They are caught between the inner asteroid belt and the distant Kuiper Belt, slowly moving from one to the other over millions of years. Their orbits are short-lived, their compositions varied, and their surfaces colored by long exposure to cosmic radiation. They are some of the more enigmatic small bodies in the solar system. Now, gently, we will turn from the rocky and icy small bodies of the asteroid family to the great cosmic visitors of the comets, the dirty snowballs of the outer solar system that occasionally drift inward toward the warm domain of the Sun. Comets are small icy bodies that originate in the cold outer regions of the solar system. They are sometimes called dirty snowballs because they are composed mostly of water ice mixed with dust and various organic compounds. When a comet drifts close enough to the Sun, the surface ice begins to vaporize, creating the brilliant glowing coma and the long flowing tail that has fascinated human observers for thousands of years. The solid central body of a comet is called the nucleus. Comet nuclei are typically small, ranging from about 100 meters to a few tens of kilometers across. The largest known comet nucleus, called Bernardinelli-Bernstein, is about 120 kilometers across, far larger than most comet nuclei. Most comet nuclei are dark and irregular, shaped like potatoes or peanuts. The composition of a comet nucleus is mostly water ice, with smaller amounts of carbon dioxide ice, carbon monoxide ice, methane ice, and ammonia ice. Mixed throughout the ice are fine particles of dust and organic compounds. The dust gives the comet its characteristically dark surface. Most comet nuclei reflect only about 4% of the sunlight that reaches them. When a comet is in the deep outer solar system, far from the sun, its surface remains frozen and quiet. Only when the comet approaches within about 5 astronomical units of the sun, roughly the distance of Jupiter, does the surface ice begin to vaporize. As the vapor escapes, it carries dust particles with it, creating a temporary atmosphere of gas and dust around the nucleus called the coma. The coma can become enormous as a comet approaches the sun. The coma of a typical active comet may grow to a diameter of 50,000 to 100,000 kilometers, roughly the size of Jupiter. The coma of the great comet Hale-Bopp in 1997 was several million kilometers across, larger than the entire planet Saturn. Beyond the coma extends the comet's tail. Most comets actually have two distinct tails. One is called the dust tail, made of fine particles released from the nucleus along with the vaporizing ice. The dust tail tends to curve gently along the comet's orbital path. The other is called the ion tail, made of ionized gas pushed away from the comet by the solar wind. The ion tail always points directly away from the sun. Comets are classified into two main categories based on their orbital periods. Short-period comets have orbital periods of less than 200 years. They are believed to originate in the Kuiper Belt, the great ring of icy bodies just beyond Neptune. Most short-period comets orbit the Sun in elongated paths that bring them periodically into the inner solar system. Long-period comets have orbital periods of more than 200 years, sometimes reaching tens of thousands or even millions of years. They are believed to originate in the much more distant Oort Cloud, the vast spherical shell of icy bodies that surrounds the entire solar system. Long-period comets can arrive from any direction in the sky, reflecting the spherical distribution of their distant home. The first close-up images of a comet nucleus were taken by the European Space Agency spacecraft Giotto in 1986. Giotto flew through the coma of Halley's comet during its passage through the inner solar system, taking detailed photographs of the dark, irregular nucleus. The images revealed for the first time the true shape and surface of a comet nucleus. Since then, several other spacecraft have visited comets at close range. The NASA mission Deep Impact deliberately struck the nucleus of Comet Tempel 1 in 2005, releasing a plume of subsurface material that was studied by accompanying instruments. The mission Stardust collected samples of dust from the coma of Comet Wild 2 and returned them to Earth in 2006. The most ambitious comet mission to date was Rosetta, the European Space Agency probe that orbited Comet 67P/Churyumov-Gerasimenko for more than 2 years between 2014 and 2016. Rosetta deployed a small lander called Philae onto the surface of the comet, the first soft landing ever achieved on a comet nucleus. The mission produced a detailed catalog of the comet's surface, composition, and behavior. Rosetta revealed that the Comet 67P has a strange double-lobed shape, sometimes called a rubber duck shape. The two lobes are connected by a narrow neck. The shape suggests that the comet formed when two smaller bodies came together gently in the early solar system and stuck together, becoming a single compound nucleus that has remained intact for billions of years. Each time a comet passes near the Sun, it loses some of its mass to vaporization. A typical comet may lose between 0.1% and a few percent of its mass during a single close approach. Over many orbits, a comet gradually shrinks. Eventually, after thousands or millions of orbits, the comet may exhaust its remaining ice and become an inactive rocky body, indistinguishable from an ordinary asteroid. Some comets do not survive their close approach to the Sun. The intense heat and gravitational forces near perihelion can break a comet into multiple pieces. The comet Shoemaker-Levy 9 famously broke into more than 20 fragments before colliding with Jupiter in 1994. Many other comets have fragmented during close approaches to the Sun, sometimes producing chains of smaller pieces that gradually disperse. Other comets disappear entirely, vaporizing completely as they pass too close to the Sun. The sun-grazing comets, called the Kreutz family, are particularly prone to this. Hundreds of small Kreutz comets have been observed approaching the Sun and vanishing into the bright corona, too small or too fragile to survive the encounter. The brightest known comet ever observed was the Great Comet of 1843. It became so bright that it was visible in daylight for several days near its closest approach to the Sun. The dust tail extended across the sky for more than 2 astronomical units, the same distance as from Earth to Mars at closest approach. Such bright comets remain among the most spectacular astronomical events ever witnessed by human eyes. Now gently, we will move closer to one of the most famous comets in human history, the patient, long-orbiting visitor known as Halley's Comet, returning to our skies once every 76 years. Halley's Comet is perhaps the most famous comet in human history. It is a short-period comet that returns to the inner solar system once every 75 to 76 years. Its long history of observed appearances stretches back at least 2,200 years, making it the most thoroughly tracked single celestial body in recorded astronomy. The comet is named after the English astronomer Edmund Halley, who in 1705 carefully studied the orbits of several comets observed in the previous century. Halley noticed that the comets observed in 1531, 1607, and 1682 appeared to follow nearly identical orbital paths. He correctly concluded that these were not 3 different comets, but a single comet returning every 76 years. Halley predicted that the same comet would return again in 1758 or 1759. He died in 1742, 16 years before his prediction could be tested. When the comet did return on schedule on Christmas night of 1758, it was named in his honor as a tribute to the first successful prediction of a periodic comet's return. Records of Halley's Comet have been traced back through history. It was observed by Chinese astronomers as early as 240 BCE and by Babylonian astronomers in 164 BCE. The comet appears in the Bayeux Tapestry, where it was depicted as an omen during the events leading up to the Battle of Hastings in 1066. It was observed by the great Italian artist Giotto in 1301 and inspired his depiction of the Star of Bethlehem in his Adoration of the Magi fresco. The orbit of Halley's comet is highly elongated. At its closest approach to the Sun, called perihelion, it comes within about 88 million kilometers, closer than the orbit of Venus. At its farthest point from the Sun, called aphelion, it travels out to about 35 astronomical units beyond the orbit of Neptune. The journey from perihelion to aphelion and back again takes approximately 76 years. The orbit of Halley's comet is also retrograde. This means it travels around the Sun in the opposite direction to all of the planets. The retrograde nature of Halley's orbit is one of several pieces of evidence suggesting that the comet originated in the distant Oort Cloud, where orbits can have any orientation, and was later captured into its current shorter period orbit by a close encounter with one of the giant planets. During its 1986 perihelion passage, Halley's comet became the first comet ever to be visited by spacecraft. An international flotilla of probes flew past the comet within a few weeks of each other. The Soviet probes Vega 1 and Vega 2, the Japanese probes Suisei and Sakigake, and the European probe Giotto all studied the comet at close range. Together, the probes returned the first detailed measurements of a comet nucleus. Giotto came closest to the comet, passing within just 600 kilometers of the nucleus. Despite the dust impacts that damaged the spacecraft, Giotto returned spectacular images that revealed for the first time the dark, irregular shape of a comet nucleus. The Halley nucleus turned out to be about 15 by 8 kilometers in size, shaped roughly like a peanut, with two distinct lobes separated by a narrow neck. The surface of the Halley nucleus is dark, reflecting only about 4% of the sunlight that reaches it. Active jets of vapor and dust emerge from a few specific surface regions where the underlying ice is exposed. Most of the surface is covered by a dark, insulating layer of dust that has been accumulated over many close approaches to the Sun. Halley's comet is now traveling outward from the inner solar system, having passed through perihelion in 1986. It will reach aphelion, its farthest point from the Sun, in 2023. After that, it will begin its slow return journey toward the inner solar system. Its next perihelion passage is expected in 2061, about 36 years from now. The next return of Halley's comet in 2061 is expected to be a particularly favorable apparition. The geometry of the comet's orbit relative to Earth at that time will allow for excellent viewing conditions. The comet should become bright enough to be easily visible to the unaided eye and may even cast a faint shadow under perfectly dark skies. Like all comets, Halley loses some of its mass each time it passes the Sun. Astronomers estimate that the comet has been losing about 1 to 3 meters of surface material from each side during every perihelion passage. At this rate, the comet should remain active for many tens of thousands of years to come, returning faithfully to the inner solar system once every 76 years for the foreseeable cosmic future. Halley's comet is also responsible for 2 annual meteor showers visible from Earth. The Eta Aquariid meteor shower in early May and the Orionid meteor shower in late October both occur when Earth passes through trails of dust left behind by Halley during its many previous orbits. The dust grains burn up gently in Earth's upper atmosphere, producing the brief streaks of light called shooting stars. In addition to its scientific importance, Halley's Comet has had a profound cultural influence. Generations of human observers have anticipated, witnessed, and recorded its returns. Mark Twain, the great American writer, was born in 1835 during the previous return and famously predicted that he would die during the next return, which he did in 1910, the day after Halley reached perihelion. Each generation of humans typically witnesses Halley's Comet either once or twice. Most see it only a single time, near the start or end of their lives. A small, fortunate group sees it twice, once in childhood and once in old age. The comet is, in this sense, a cosmic timekeeper marking the cycle of human generation. Tonight, Halley's Comet is far away in the distant outer solar system, beyond the orbit of Neptune, slowly turning back toward the warmth of the sun. It will continue its quiet, patient journey for the next 36 years before becoming visible again to human eyes. Until then, it remains in the cold dark of deep space, exactly where it has been for the last several decades. Now, gently, we will move from the patient, regular Halley's Comet to the spectacular great comets, the rare, brilliant visitors that arrive only once in a generation, lighting up the cosmic sky for a few brief weeks before vanishing into the deep dark for thousands of years. A great comet is a comet that becomes exceptionally bright in the cosmic sky, bright enough to be easily seen with the unaided human eye, sometimes even visible during daylight. Great comets are quite rare. On average, only about 1 or 2 truly great comets appear per century. Each one becomes a cultural event of its time, witnessed by millions of human observers. There is no formal scientific definition of a great comet. Whether a comet qualifies depends on a combination of factors: the intrinsic brightness of the comet itself, the closeness of its approach to the sun, the closeness of its approach to Earth, the geometry of its tail, and the latitude of observers all contribute to whether a particular comet is widely seen as great. One of the greatest comets of recent decades was Comet Hyakutake, discovered in late January of 1996 by the Japanese amateur astronomer Yuji Hyakutake. The comet passed extraordinarily close to Earth, only about 15 million kilometers away, less than a tenth of the distance from Earth to the Sun. From dark sky locations, Hyakutake was visible to the unaided eye with a tail that stretched across more than half the sky. Hyakutake was a long-period comet from the distant Oort Cloud. Its orbital period is estimated to be roughly 70,000 years, meaning that the comet last visited the inner solar system long before the dawn of human civilization. After its 1996 passage, gravitational interactions with the giant planets lengthened its orbit further. The comet will not return again for at least 100,000 years. The very next year, an even more famous comet appeared. Comet Hale-Bopp was discovered in 1995 by 2 American observers, Alan Hale and Thomas Bopp, independently noting it on the same night while observing in different states. Although Hale-Bopp did not pass nearly as close to Earth as Hyakutake, it had an exceptionally large nucleus, perhaps 60 kilometers across. This made it intrinsically very bright. Hale-Bopp became visible to the unaided eye for an unprecedented 18 consecutive months, from May 1996 through November 1997. It became one of the most observed comets in human history. The comet had 2 distinct tails, a blue ion tail and a yellow-white dust tail, that were visible simultaneously to anyone observing under a clear, dark sky. The orbital period of Hale-Bopp is approximately 2,530 years. Its previous visit to the inner solar system was around the time of ancient Egypt and the early Bronze Age civilizations. Its next visit is expected in the year 4385. Many human generations from now, Hale-Bopp will return as another great cosmic visitor. Another remarkable recent great comet was Comet McNaught, discovered in 2006 by the Scottish-Australian astronomer Robert McNaught. It became the brightest comet in more than 40 years. From the southern hemisphere, McNaught displayed an enormous fan-shaped dust tail that astronomers compared to the spread feathers of a peacock. The northern hemisphere also saw a beautiful curving tail at twilight. Comet Neowise in 2020 was another great comet that surprised many observers. Discovered by NASA's Neowise Space Telescope in March of that year, the comet survived its close approach to the Sun and emerged as a bright cosmic visitor in the northern hemisphere skies during July. Many people who had been confined to their homes that summer made memorable trips outside to view the comet during its brief visit. Going back further in history, the Great Comet of 1843 was perhaps the most spectacular comet of the 19th century. It approached extraordinarily close to the Sun, passing within about 800,000 kilometers of the solar surface, far closer than even the closest planet, Mercury. It survived this incredibly close passage and emerged with an enormous tail more than 2 astronomical units long. The Great Comet of 1882 was another spectacular sun-grazing comet. It survived its close approach to the Sun and developed a magnificent tail visible to observers around the world. The comet was so bright that it was clearly visible to the naked eye even when standing close to the rising or setting sun. The early 20th century saw the Great Comet of 1910, which appeared just months before the spring return of Halley's comet. Many observers initially confused the two events. The Great January Comet of 1910 was actually brighter than Halley's later return and produced one of the most brilliant comet displays of the 20th century. Comet Hygiea in 1965 was perhaps the most extraordinary great comet of the 20th century. It was a sun-grazing Kreutz family comet that passed within just 450,000 kilometers of the Sun's surface, closer than any spacecraft. It survived the encounter and produced a tail estimated at more than 1 astronomical unit long. At its peak, the comet was bright enough to be easily seen during full daylight. Some great comets do not survive their close approach. The most famous example was Comet ISON in 2013. The comet had been expected to become exceptionally bright, but during its closest approach to the Sun on the 28th of November, the nucleus disintegrated. What had been a bright cosmic visitor became a dim, diffuse cloud of dust that gradually faded into invisibility. Predicting which comets will become great is notoriously difficult. Some comets that astronomers expect to be spectacular fail to brighten as predicted. Other comets, expected to remain faint, surprise everyone by becoming bright. The behavior of any individual comet depends on its specific composition, structure, and history, factors that are difficult to assess from a distance. Each great comet brings together millions of human observers in shared experience. Children look up at them in wonder. Adults remember earlier comets they saw long ago. Astronomers gather data that will be studied for decades. The brief visit of a great comet lasting only a few weeks becomes a memory that can last for an entire lifetime. Now, gently, we will move from the great comets themselves to the beautiful structure of their tails, the long flowing streams of dust and ionized gas that give comets their characteristic appearance in the cosmic sky. Every active comet that approaches close to the Sun develops a tail. In fact, most comets develop two distinct tails, one made of ionized gas and the other made of fine dust. The two tails behave very differently from each other, and they can be distinguished by their colors, their orientations in the cosmic sky, and the physics that creates them. The dust tail is made of fine, solid particles released from the comet nucleus, along with the vaporizing ice. As the ice on the surface of the nucleus turns directly from solid to vapor, a process called sublimation, it releases small grains of dust that had been embedded within the ice. The dust grains are slowly pushed away from the nucleus by the gentle pressure of sunlight. Because the dust grains are gradually pushed away rather than rapidly accelerated, the dust tail tends to lag behind the comet's motion. It curves gently along the comet's orbital path, often appearing yellowish or white because it reflects sunlight in much the same way that ordinary dust does. The dust tail is the broader and more familiar of the two tails. The ion tail is made of ionized gas. As neutral gas molecules escape from the comet, ultraviolet light from the Sun strikes them and knocks away electrons, leaving behind positively charged ions. These ions are very strongly affected by the magnetic field carried by the solar wind, the constant stream of charged particles flowing outward from the Sun. The solar wind sweeps the ions directly away from the Sun, almost regardless of the comet's own motion. The result is that the ion tail always points directly away from the Sun in a straight line that does not curve along the comet's orbit. The ion tail typically appears bluish in color because the ionized gas glows in a characteristic blue light when illuminated by sunlight. The two tails together create the classic dual tail appearance of many comets. The dust tail curves one way along the orbital path. The ion tail extends straight outward away from the Sun. The angle between them depends on the comet's exact position in its orbit and the geometry of the observer's view. Some comets also display a third feature called a sodium tail. This was first clearly observed in comet Hale-Bopp in 1997. The sodium tail consists of neutral sodium atoms released from the comet that glow with a characteristic yellow-orange color when illuminated by sunlight. The sodium tail is fainter and narrower than the dust and ion tails, and it points in yet another direction in the cosmic sky. The length of a comet tail can be enormous. The dust tail of a great comet can extend for more than 1 astronomical unit, equivalent to the distance from the Earth to the Sun. The ion tail of Comet Hyakutake in 1996 was measured at more than 500 million kilometers in length, making it one of the longest cometary structures ever observed. Despite their enormous lengths, comet tails are extraordinarily diffuse. The density of dust and gas in even a bright comet tail is far less than the density of air at the surface of the Earth. If you could somehow gather an entire cubic kilometer of comet tail, the total mass would be only a few kilograms. Comet tails are spectacular largely because they reflect and emit light efficiently, not because they contain large amounts of matter. The ion tail can sometimes show dramatic structural events called disconnection events. When the magnetic field of the solar wind suddenly changes direction, the ion tail can be disconnected from the comet head. The old ion tail drifts away while a new one slowly grows in its place. Disconnection events have been photographed in many comets and offer a beautiful glimpse into the interaction between solar wind and cometary plasma. Comet tails always change in appearance over the course of a single apparition. As the comet approaches the Sun, the tails grow longer and brighter. At perihelion, when the comet is closest to the Sun, the tails are typically at their most spectacular. As the comet moves away from the Sun, the tails gradually shrink and fade until they are no longer visible. The direction of the comet tails relative to the comet's motion can be confusing to first-time observers. Many people assume that the tail trails directly behind the comet, like the wake behind a moving boat. In fact, the orientation of the tail depends entirely on the position of the Sun, not on the direction of the comet's motion. Sometimes the tail can even appear to point ahead of the comet when the comet is moving away from the Sun. Some comets develop fan-shaped tails rather than narrow streamers. This happens when the comet is releasing dust grains of many different sizes simultaneously. Smaller grains are pushed away more quickly by sunlight, while larger grains lag farther behind. The combination produces a broad fan that spreads across a wide arc of the cosmic sky. Comet tails have been studied carefully by various spacecraft. The Ulysses spacecraft, originally designed to study the Sun, accidentally flew through the ion tail of Comet Hyakutake in 1996. The unexpected encounter allowed Ulysses to make the first direct in situ measurements of a comet ion tail far from the comet itself, providing valuable data about how the tail interacts with the solar wind. In addition to the dust tail and ion tail, some comets also display a faint feature called the antitail. An antitail is a small spike of dust that appears to point toward the Sun, opposite to the main dust tail. It is actually an optical illusion caused by Earth's perspective on the comet's orbital path. When Earth crosses the plane of the comet's dust trail at just the right angle, the trail appears edge-on as a spike. The colors and structures of comet tails make them among the most beautiful objects in the night sky when they appear. Their gentle glow against the deep cosmic dark, their slow visible motion from night to night, and their delicate fading as the comet moves on, all of these contribute to the lasting impression that great comets leave on human observers. Now gently, we will move from the comet tails themselves to a related cosmic phenomenon, the meteor showers, when small fragments left behind by comets enter the upper atmosphere of Earth and burn up in brief streaks of light. A meteor shower occurs when Earth, in its orbit around the Sun, passes through a stream of dust and small particles left behind by a comet. The particles enter Earth's upper atmosphere at very high speeds, typically tens of kilometers per second. Friction with the air heats the particles intensely, causing them to vaporize in brief streaks of light called meteors or shooting stars. The particles that produce meteors are usually very small. Most are no larger than a grain of sand. Even though the particles themselves are tiny, the streaks of light they produce can be quite bright because they are heated to such high temperatures during their brief journey through the upper atmosphere. A typical visible meteor lasts only a fraction of a second. Each annual meteor shower is associated with a specific comet that has left its dust along Earth's orbital path. The Perseid meteor shower in August comes from Comet Swift-Tuttle, The Leonid meteor shower in November comes from Comet Tempel-Tuttle, the Eta Aquariids in May, and the Orionids in October both come from Halley's comet. Meteor showers appear to radiate from a single point in the sky called the radiant. Although the meteor particles are actually traveling in parallel paths through Earth's atmosphere, the perspective effect makes them appear to diverge from a common origin point. Each meteor shower is named after the constellation that contains its radiant. The Perseid meteor shower is one of the most reliable and popular annual showers, peaking each year around the 11th and 12th of August. The radiant lies in the constellation Perseus. At its peak, observers in dark sky locations can see 50 to 100 meteors per hour. The Perseids have been observed and recorded for nearly 2,000 years. The Geminid meteor shower in December is another of the most spectacular annual showers. The Geminids peak around the 13th and December 10th. Unlike most meteor showers, the Geminids are not associated with a comet. They come from an unusual asteroid called Phaethon, which has an orbit that takes it very close to the Sun and which sheds dust in a way more typical of a comet than an asteroid. The Leonid meteor shower in mid-November is famous for occasionally producing meteor storms, brief, intense periods when meteor rates can reach thousands per hour. These storms occur when Earth passes through a particularly dense part of the dust trail left by Comet Tempel-Tuttle, which itself returns to the inner solar system once every 33 years. The most famous Leonid meteor storm occurred in 1833. The Quadrantid meteor shower in early January is named after a now-defunct constellation called Quadrans Muralis. The constellation is no longer recognized officially, but the meteor shower retains its old name. The Quadrantids peak around the 3rd and 4th of January with rates that can reach more than 100 meteors per hour during the brief peak period. The Lyrid meteor shower in April is one of the oldest known meteor showers, with records going back more than 2,700 years. The Lyrids are associated with Comet Thatcher, which has an orbital period of about 415 years. The shower peaks around the 22nd of April with moderate rates of meteors. The Eta Aquariid meteor shower in early May and the Orionid meteor shower in late October are both associated with Halley's comet. Earth's orbit crosses the dust stream of Halley twice each year, producing the two showers. The Eta Aquariids are best seen from the southern hemisphere, while the Orionids are well visible from both hemispheres. Some meteor showers are very minor, with only a few meteors per hour at their peak. Others can be major events with rates of more than 100 meteors per hour. The exact rate of any particular shower depends on the geometry of Earth's encounter with the dust stream that year, and on the specific density of dust at the location where Earth happens to cross. Occasionally, an unusually large meteor enters the atmosphere. These bright meteors are called fireballs or bolides. A fireball can be brighter than the planet Venus, and the very brightest can briefly cast shadows on the ground. Fireballs sometimes leave a glowing trail in the atmosphere that can persist for many seconds after the meteor itself has passed. Most meteors burn up completely in the upper atmosphere. They never reach the ground. The largest fragments, however, can survive their atmospheric passage and land as meteorites. Several meteor showers occasionally produce meteorite falls, although these are uncommon. Most meteorites that are recovered come from random sporadic meteors rather than from named showers. Modern observations of meteor showers use a combination of visual observation, photography, video monitoring, and radar. Radar can detect meteors during the day and through clouds, allowing astronomers to monitor meteor activity continuously. Video monitoring networks across multiple countries record meteor trails simultaneously, allowing the precise three-dimensional path of each meteor to be reconstructed. Meteor showers also have a long cultural history. Throughout human history, observers around the world have noticed and recorded the annual recurrence of these brief streaks of light. Many cultures developed mythological explanations for the showers, often associating them with natural cycles, with the spirits of the dead, or with omens of various kinds. Night. Somewhere on Earth, small dust grains are entering the atmosphere from cosmic space. Some of them produce visible meteors, drawing brief lines of light across the cosmic dark. Most of them are too small or too dim to be seen by anyone. The slow, steady rain of cosmic dust on our planet has been continuing quietly for 4.5 billion years and will continue for billions more. Now, gently, we will move outward from the meteor showers into the deep outer solar system to visit the Great Kuiper Belt, the wide ring of icy bodies that lies just beyond the orbit of Neptune. The Kuiper Belt is a vast ring of icy bodies that orbits the Sun beyond Neptune. It begins at about 30 astronomical units from the Sun just past Neptune's orbit and extends to roughly 50 astronomical units. The belt is named after the Dutch-American astronomer Gerard Kuiper, who suggested in 1951 that such a population of icy bodies should exist beyond the planet. The first body of the modern Kuiper Belt was discovered in 1992. Two American astronomers, David Jewett and Jane Liu, identified a small, distant icy body about 200 kilometers across, slowly orbiting the Sun far beyond Neptune. The body was given the provisional designation 1992 QB1. Today it is also known by its formal name, Albion. Since the discovery of Albion, more than 3,000 Kuiper Belt objects have been identified. The total population of bodies larger than 100 kilometers is estimated to be in the hundreds of thousands. The total mass of all Kuiper Belt objects combined is thought to be roughly 1/10 the mass of Earth. Small compared to a planet, but vast compared to the main asteroid belt. The most famous resident of the Kuiper Belt is Pluto. Discovered in 1930 by the American astronomer Clyde Tombaugh, Pluto was originally classified as the 9th planet of the solar system. After the discovery of many other Kuiper Belt objects of similar size, Pluto was reclassified in 2006 as a dwarf planet, the same category as Ceres in the main asteroid belt and Eris in the more distant scattered disk. Pluto is roughly 2,370 kilometers across, about 2/3 the size of our Moon. It has a thin, nitrogen-rich atmosphere, a varied surface with mountains of frozen water ice and plains of nitrogen frost, and at least 5 known moons. The largest moon, Charon, is about half the size of Pluto itself, making the Pluto-Charon system more like a binary dwarf planet than a planet with a moon. In 2015, the New Horizons spacecraft made the first close-up flyby of Pluto. After a journey of more than 9 years from Earth, New Horizons passed within 12,500 kilometers of Pluto's surface. The spacecraft captured spectacular images that revealed Pluto to be a complex active world with surprising geological features, including the heart-shaped frozen nitrogen plain known as Sputnik Planitia. Beyond Pluto, the Kuiper Belt is home to several other dwarf planets. Haumea is a strange football-shaped body about 1,700 kilometers along its longest axis. It rotates once every 4 hours, one of the fastest rotation rates known in the solar system. The rapid rotation has stretched Haumea into its elongated shape. Haumea also has 2 small moons and a faint ring system. Makemake is another Kuiper Belt dwarf planet, about 1,400 kilometers across. It was discovered in 2005 and named after a creator figure from the mythology of the Rapa Nui people of Easter Island. Makemake has a thin atmosphere when it is closer to the Sun in its orbit, and one known small moon called Mk2. Eris is the largest known dwarf planet, slightly larger than Pluto. It was discovered in 2005 by an American team led by Mike Brown. Eris orbits the Sun much farther out than Pluto, sometimes at more than 90 astronomical units. The discovery of Eris and the realization that other Pluto-sized bodies must exist in the outer solar system led directly to the redefinition of the term planet and the creation of the dwarf planet category. Many Kuiper Belt objects orbit the Sun in carefully resonant patterns with Neptune. The most famous resonance is the 3:2 resonance, where the object completes 2 orbits around the Sun for every 3 orbits of Neptune. Pluto itself follows this resonance. Other resonant orbits include the 2:1 and the 5:3 patterns. The resonant orbits provide stability over very long periods of time. Beyond the main Kuiper Belt lies a more diffuse population called the scattered disk. Scattered disk objects have orbits that are typically more elongated and more tilted than those of the main belt. They are believed to have been gravitationally scattered into their current orbits by interactions with Neptune in the early solar system. Eris is one of the largest scattered disk objects. The most distant known Kuiper Belt object visited by spacecraft is called Arrokoth. The New Horizons spacecraft, having completed its primary mission at Pluto, continued outward and made a close flyby of Arrokoth on New Year's Day of 2019. Arrokoth is a small contact binary about 36 kilometers long, shaped like a flat snowman with 2 distinct lobes joined at a narrow neck. The 2 lobes of Arrokoth are remarkably flat, the larger lobe like a pancake and the smaller one like a walnut. Astronomers believe Arrokoth formed when 2 slowly drifting bodies came together gently in the early solar system. The flatness of the lobe suggests that the original material was assembled gradually from many smaller fragments rather than from a violent cosmic impact. Most Kuiper Belt objects are reddish in color. The redness is believed to come from organic compounds on the surface that have been processed by long exposure to cosmic radiation. The deepest red objects, sometimes called the cold classical Kuiper Belt objects, are the most pristine, preserving the original chemistry of the early outer solar system. The Kuiper Belt is also the source of the short-period comets that visit the inner solar system. Slow gravitational interactions with the giant planets gradually push some Kuiper Belt objects inward. They first become Centaurs, drifting between Jupiter and Neptune. Then some are pushed further inward by additional gravitational nudges, and they enter shorter orbits that bring them periodically into the realm of the inner planets. Tonight, the Kuiper Belt remains as it has been for 4.5 billion years, a vast, quiet ring of icy bodies orbiting in the cold dark beyond Neptune. The dwarf planets continue their slow turning. The smaller bodies drift in their long orbits. Sunlight at the Kuiper Belt is faint, only about 1/1000th the intensity it has at Earth, but it is enough to keep the cosmic darkness gently illuminated. Now gently, We will travel even farther outward, to the very edge of the Sun's quiet domain, to the vast spherical Oort Cloud, which surrounds our entire solar system in a great shell of distant icy bodies. The Oort Cloud is the most distant region of the solar system. It is a vast spherical shell of icy bodies that surrounds the Sun and all of the planets, extending from perhaps 2,000 astronomical units out to as much as 100,000 astronomical units. At its outer edge, the Oort Cloud reaches nearly halfway to the nearest star, Proxima Centauri. The Oort Cloud is named after the Dutch astronomer Jan Oort, who proposed its existence in 1950. Oort noticed that long-period comets entering the inner solar system seemed to come from a wide spherical distribution rather than from any preferred direction. He suggested that there must be a great spherical reservoir of comets at the very edge of the solar system, occasionally sending small numbers of bodies inward toward the Sun. The total number of bodies in the Oort Cloud is estimated to be enormous, perhaps 1 trillion icy objects larger than 1 kilometer across. The total mass of all of these bodies combined may be roughly 5 Earth masses. Most of the Oort Cloud is so far away that the light from the Sun takes weeks or even months to reach the most distant bodies. The Oort Cloud is divided conceptually into 2 regions. The inner Oort Cloud, sometimes called the Hills Cloud, extends from about 2,000 to 20,000 astronomical units. The outer Oort Cloud extends from 20,000 astronomical units out to roughly 100,000 astronomical units. The outer cloud is more spherical, while the inner cloud is somewhat more disc-shaped, perhaps a remnant of the original protoplanetary disk. The bodies of the Oort Cloud are extraordinarily distant from each other. The typical distance between 2 adjacent Oort Cloud objects is many tens of millions of kilometers. The cloud is so vast and so empty that any individual object spends almost all of its time alone in the deep cosmic dark, never seeing another solid body for billions of years at a time. Sunlight at the Oort Cloud is extraordinarily faint. The Sun would appear as a single bright star, no different in apparent size from many of the brighter stars in our sky. From the outer edge of the Oort Cloud, the Sun is roughly 20,000 times fainter than it appears from Earth, still bright enough to be the brightest object in the cosmic sky, but not bright enough to provide any meaningful warmth. Temperatures in the Oort Cloud are extremely cold. Surface temperatures of bodies there are estimated to be only about 4 degrees above absolute zero. At these temperatures, all of the volatile compounds, water, methane, carbon dioxide, ammonia, are completely frozen solid. The Oort Cloud bodies are essentially time capsules, preserving the original chemistry of the very early outer solar system. The Oort Cloud is believed to have formed in the early solar system when the giant planets were still moving through their final orbital arrangements. Many small icy bodies that originally formed in the region of the giant planets were gravitationally scattered outward into very large orbits. Some were ejected from the solar system entirely. Others settled into the long elliptical orbits that today form the Oort Cloud. Once in the Oort Cloud, the orbits of these bodies are extremely long. A typical Oort Cloud comet completes one orbit around the Sun in millions of years. Some take tens of millions of years for a single orbit. The bodies move very slowly through their distant orbits, traveling only a few meters per second at their farthest points from the Sun. Although the Oort Cloud bodies are mostly stable in their distant orbits, they are subject to occasional gentle gravitational perturbations. Three main sources of perturbation can disturb their orbits. Passing stars traveling through nearby space can give a small body a gentle gravitational nudge. Galactic tides, the slow gradient of gravitational pull from the rest of the Milky Way galaxy, can also slowly modify orbits. Finally, occasional close encounters with giant molecular clouds can also affect the cloud. Each of these gentle perturbations can change the orbit of an Oort cloud body. In some cases, the new orbit takes the body further out into the cosmic dark, sometimes ejecting it from the solar system entirely. In other cases, the new orbit brings the body inward on a long, quiet trajectory toward the inner solar system. Eventually, after thousands or millions of years of slow inward travel, the body may arrive in the inner solar system as a long-period comet. The arrival of a long-period comet in the inner solar system is a relatively rare event. On average, only a few new long-period comets enter the inner solar system each year. Most of these are small and faint, never becoming bright enough to be visible without a telescope. A small number, however, become great comets that dominate the cosmic sky for a few weeks before retreating back to the deep cosmic dark. The most distant known object in the Oort cloud is currently a body called 2014 UZ224, sometimes nicknamed the Goblin. It was discovered in 2018 and orbits the Sun at an average distance of about 380 astronomical units. The Goblin is one of the few inner Oort cloud objects ever directly observed. The Oort cloud has never been visited by spacecraft. The most distant active spacecraft, Voyager 1 and Voyager 2, are currently at distances of about 160 astronomical units from the Sun, well beyond the orbit of Pluto, but still far short of the inner edge of the Oort cloud. Even at their current speeds, the Voyagers will take roughly 300 years to reach the beginning of the Oort cloud and tens of thousands of years to traverse it. The Oort cloud is also believed to be the source of all the great comets that visit our skies. Hyakutake, Hale-Bopp, McNaught, Neowise, all of these spectacular cosmic visitors began their long journey inward from the Oort cloud, falling slowly toward the Sun for thousands of years before brightening briefly and then disappearing again into the deep dark. Tonight, the Oort cloud surrounds our entire solar system in a quiet sphere of distant icy bodies. The Sun from out there is just one of countless points of light in the cosmic sky. The bodies drift in their long elliptical orbits, mostly never moving far from where they have been for billions of years. The cloud is patient, vast, and beautifully empty, the quiet outer edge of the Sun's gentle gravitational influence. Now, gently, we will turn from the distant Oort cloud back inward to consider the cosmic visitors that have actually reached our world over geological time, the famous impacts and the rare close approaches that have occurred throughout Earth's long, quiet history. Throughout the long history of the solar system, comets and asteroids have occasionally collided with planets, moons, and other small bodies. The vast majority of these impacts happened in the distant past during the early formation of the solar system, when small bodies were far more numerous than they are today. Today, large impacts are very rare, although small ones happen continuously. The most famous historical impact in human memory was the Tunguska event of 1908. On the morning of June 30th that year, an enormous explosion occurred in a remote forest of Siberia near the Tunguska River. The blast flattened roughly 2,000 square kilometers of forest, knocking down an estimated 80 million trees. The seismic shock wave was detected as far away as Western Europe. Despite the enormous energy of the Tunguska explosion, no impact crater was ever found. The cosmic body that caused the event is believed to have been a small asteroid or comet fragment, perhaps 50 to 100 meters across. It exploded in the upper atmosphere, several kilometers above the surface, releasing its energy as a powerful airburst rather than as a ground impact. Tunguska is widely regarded as the best example of a small impactor entering Earth's atmosphere in modern history. Had it occurred over a populated area instead of a remote forest, it would have caused enormous devastation. Fortunately, the Earth is mostly ocean and uninhabited land, so even when small cosmic bodies do reach the surface, they almost always strike places where they cause minimal harm. More than a century after Tunguska, on February 15th in 2013, another small cosmic body entered Earth's atmosphere over the city of Chelyabinsk in Russia. This body was a small asteroid about 20 meters across, much smaller than the Tunguska impactor. It also exploded in the upper atmosphere, but its airburst released energy equivalent to about 500 kilotons of TNT. The Chelyabinsk event was extensively recorded by car dashboard cameras, which were widely used in Russia at the time. The footage allowed scientists to reconstruct the trajectory and behavior of the bolide in unprecedented detail. The event injured around 1,500 people, mostly from broken glass when the shock wave shattered windows across the affected region. Going much further back in time, perhaps the most famous impact in Earth's geological history occurred about 66 million years ago. A large asteroid or comet, perhaps 10 to 15 kilometers across, struck what is now the Yucatan Peninsula in Mexico. The impact created the Chicxulub crater, more than 150 kilometers across, and is widely believed to have caused the extinction of the dinosaurs, along with about 3/4 of all species on Earth at the time. The Chicxulub crater itself is now buried beneath kilometers of younger rock and sediment, having been quietly covered over by the slow processes of geology. It was first identified by careful gravitational and magnetic surveys in the late 20th century. Drill cores taken from the crater have confirmed its impact origin and have provided detailed information about the catastrophic event. Other large impact craters are visible on the surface of Earth today. The Vredefort crater in South Africa is the largest known impact structure on Earth, more than 200 kilometers across. It formed about 2 billion years ago. The Sudbury Basin in Canada and the Chicxulub crater in Mexico complete the top three. Hundreds of smaller impact craters have been identified worldwide, ranging from a few meters to many kilometers in diameter. The Moon, with its lack of atmosphere and lack of weathering processes, preserves a much more complete record of cosmic impacts than the Earth. The lunar surface is covered with millions of craters of all sizes. The youngest large craters on the Moon, such as Tycho and Copernicus, are visible from Earth with binoculars or a small telescope. The most famous comet impact in human memory occurred in 1994, when fragments of Comet Shoemaker-Levy 9 collided with Jupiter. The comet had been broken into more than 20 pieces by Jupiter's gravity during a previous close approach. When the fragments returned, they crashed into Jupiter's atmosphere one by one over the course of several days, producing enormous dark scars in the Jovian cloud tops that were visible from Earth with even small telescopes. The Shoemaker-Levy 9 impacts demonstrated dramatically that comets can and do hit planets in the modern solar system. The energy released by the largest fragments was equivalent to roughly 6 million megatons of TNT, vastly more than any nuclear weapon ever made. The dark scars in Jupiter's atmosphere persisted for many months before slowly fading. On much smaller scales, small fragments of asteroids and comets fall to Earth as meteorites every year. Several thousand meteorites are recovered annually, although only a small fraction are observed during their actual fall. Most are found later through systematic searches, especially in places like Antarctica, where dark meteorites stand out clearly against the white ice. Some meteorites have remarkable origins. A small fraction of all known meteorites have been positively identified as coming from Mars, ejected from the Martian surface by ancient impacts, and then traveling through deep space for millions of years before reaching Earth. Other meteorites have been identified as coming from the Moon, also ejected by impacts. These special meteorites are pieces of other worlds, gently delivered to Earth by the slow workings of the cosmos. In recent years, two cosmic bodies have been identified that did not originate in our own solar system. Comet I-1/Oumuamua was discovered in 2017. Comet I-2/Borisov was discovered in 2019. Both bodies were on hyperbolic trajectories that revealed they had come from interstellar space and would continue back into interstellar space after their brief visits to the inner solar system. These interstellar visitors were the first definitively detected objects from outside our solar system. Their existence confirms that other star systems also produce small bodies, and that some of these bodies occasionally drift through the vast reaches of interstellar space, eventually passing close to other stars. Our own solar system has likely also ejected many such bodies into interstellar space over its long history. Tonight, comets and asteroids continue their long, quiet existence across the solar system. Most of them will never come close to any planet. Most of them will simply continue their patient orbits as they have for billions of years. They are some of the oldest unchanged bodies in the cosmos, quiet remnants of the same materials from which all the planets formed. Thank you for being here through this long, quiet journey. If sleep is finding you, then we have done what we set out to do tonight. Subscribing keeps these visits coming, week after week, always through the slow places of the cosmic world of comets and asteroids, always at this unhurried pace. Good night from all of us at the Circadian Institute. We hope sleep is finding you. The small bodies of the asteroid belt are still drifting in their long, quiet orbits between Mars and Jupiter tonight. The icy comets of the Kuiper Belt are still circling the distant, cold outer reaches of the solar system. The Oort Cloud is still surrounding our entire planetary neighborhood in a vast spherical shell of patient ice, exactly as it has for ages. They will continue, whether you are awake or asleep. Tonight, you can let yourself drift. Good night. And with that, we bring tonight's quiet journey through the comets and asteroids of the solar system to a soft close. The asteroid belt is still quietly drifting between Mars and Jupiter. The comets are still patient in the cold outer dark. The Oort Cloud is still surrounding our entire solar system in a vast spherical shell of icy bodies. They will all continue without us. Sleep softly tonight.